Chapter 13 is on kinetics. Kinetics, as the word itself suggests, has got something to do with speed of the reaction. Speed. How fast, how slow a certain reaction is occurring, because optimum speeds is what we are seeking, and I'll talk about that in a second. But every time I think about chemical kinetics or speeds of reaction, I'm reminded of my time in graduate school when I had a fellow student who had this habit of chasing lizards whenever he could, and he would just spray cold water onto those lizards, and so the lizards would get a little immobilized, and then he would catch them, and then he would just let them go. And he would do that again. So anyway, but what's happening in there? Essentially, the immobilization of the lizard is occurring because, unlike human beings that are warm-blooded, lizards are cold-blooded. So their body temperature is dependent on the temperature of the surrounding. And so if you spray them with cold water, their body temperature is going to drop, and the speed with which the muscles move, that is going to slow down too, and they are going to get into this mode of lethargy, if you will. And so, of course, slower motion, and he would be able to catch it. So anyway, I just thought that story was interesting. Anyway, so what I was trying to talk about earlier, realize it really is important for any chemical reaction to go through at an optimum pace. And of course, how fast or how slow really is dependent on the reaction in question. If you have to run a reaction, you have let's say, a pharmaceutical drug that you are trying to prepare, any time ranging from 10 minutes to 48 hours is a good time. Okay. On the other hand, if you're thinking about a reaction, let's say it's the thrust, that a rocket gets during the rocket launch from the burning of the fuels. What happens there? You can think about it as, if it's too quick, the combustion is too fast, it can actually generate too much heat all of a sudden, and you're going to see an explosion of the rocket. On the other hand, if it's too slow, then it's not going to leave the ground. So it really depends on, your situation, what reaction you're referring to, and the fast and the slow is decided based upon that. So how do we define rate of a reaction? How do we measure it? That's what we are going to learn in this chapter. Chemical kinetics, like I said, is a study of reaction rate. So when I say rates, I basically mean speed with which the concentration of the reactants decreases, because reactants are becoming products for any general reaction. Let's say A plus B gives you C plus D. One can say that the reactants are being used up and products are being formed. So over a period of time, you can envision that the amount or the concentration of A and B is going to decrease, and C and D, since it's a product, it's going to increase. So realize that we are measuring concentrations. And you could do that for either the reactants or the products. Okay? Like we were discussing earlier, it's really important to be able to control the rates of the reaction. If it's too quick or if it's too slow, that you can't measure it, you can't control it, sometimes it could be a safety hazard as well. And then in this chapter, we are also going to discuss the various different factors that influence the rate. And some of those are the concentration of the reactants. So this is usually measured as molar concentration or molarity, so capital M. Nature of the reaction, so what's the mechanism, how does it occur? Temperature of the reaction, that's an important one. Presence or absence of a catalyst. So we are going to take a look at each of those in a little bit more detail at a later time, but this is what we are going to discuss in this chapter. So let's first discuss reaction rate and how do we measure it. Just like we say speed, in regular day-to-day life, speed is displacement over time, the distance that you travel in a certain direction over time. right? So the change of distance with respect to time. So one say dx by dt, for example, if you were a differential analysis student. In this case, we are saying this is speed of the reaction. So we are saying it's going to be the change in concentration per unit time. Okay, now depending on which component you're writing the rate for, the expression is going to look different. Let's see how. Let's say we talk about a general reaction N2O5 giving you 2NO2 plus half O2. First of all, this should be a balanced equation, so make sure you verify that the equation you're given is balanced. In this case, it is. And you can see one thing is becoming many, so this must be a decomposition reaction. And now if I had to figure out the rate of the reaction in terms of N2O5, what would I say? You can say, well, over a period of time, N2O5, the concentration is going to decrease. And if you think about NO2, which is a product, the concentration is going to increase. Same is the case for the oxygen gas as well. But if somebody has to read the reaction, what is the relative rate with respect to each other, you would say that as 1 mole of N2O5 decomposes, 2 moles of NO2 get formed and half a mole of oxygen gets produced as well. So could I say that whatever is the change that is occurring in the concentration of N2O5, the concentration is always going to be written in square parentheses, which shows the molar concentration or moles per liter. The delta signifies the change in concentration. So whatever is the change in concentration for N2O5, that divided by the change in time, so the time interval that you're using, that is going to signify the rate with respect to N2O5. I'm missing one thing right now. I always will write it with a negative sign. The negative sign only tells you that this must be a reactant. That means the concentration is going to decrease over a period of time. That's all that it tells you. It actually is a positive value. If you had to write the same thing for NO2 now, realize as 1 mole of N2O5 decomposes, 2 of NO2 get formed. So if you were to actually get the concentration, you can say that essentially the change in concentration or the speed with which N2O5 decomposes, that's half that of NO2. And where did that half come from? That half came from the 2 that you have right in front of your NO2. So you can say that the rate is going to look like delta NO2 divided by 2 times delta T. And when we have to, this of course comes with a positive sign because this is a product. If you have to do the same thing for oxygen, you would say change in the concentration of oxygen divided by delta T. And of course, my stoichiometric coefficient here is half. So that's what I'm going to put in the denominator. And that becomes my rate expression written in terms of the reactants as well as the products. Hopefully it's so far so good. So hopefully I have been able to tell you, I have been able to put the point across that when you are thinking about rate of a chemical reaction and you're measuring how fast or how slow a certain reaction is going, a rate, just like we say for speed, it's the change in distance over time. If your doctor says, make sure your weight loss is at a suitable rate, don't overexert yourself, that would be the change in weight, again, per unit time. In this case, we are talking about the change of concentration of the reactant or the product per unit time. So if you knew the time interval, if you knew some information about the concentrations, or you could measure that experimentally, you should be in a good position to determine the rate of the reaction. If you're talking about a reactant, that value is usually shown with a negative sign. If on the other hand you have the product, you use essentially a positive sign. Notice the 2 in front in case of NO2 and the half in case of oxygen come from the stoichiometric coefficient that you have, that basically is giving you an idea that anytime you run this reaction for a balanced equation, so let's say you multiply it by 10, okay? So you're running this for 10 moles of the N2O5. That automatically would mean that you're going to generate 20 moles of NO2 and you're going to generate 5 moles of oxygen gas, so that's automatic. But the speed with which it's going to occur, essentially, that is, it's the rate of the reaction. And so the concentration of, when you read this balanced equation, one can safely say that the concentration of NO2 increases at twice the rate of the concentration at which the N2O5 decomposes, or you can say that the speed with which oxygen gets formed is half the speed with which N2O5 decomposes. So if you were to kind of plot it out, if you were to graph it out and you had, let's say, concentration, and you were plotting that against time or reaction progress, if you were thinking about the reactants, they're going to go in this direction. They decrease. Reactants. Products, they always will increase, unless they reach a state where they become kind of constant. That is the state that we say that an equilibrium has been achieved. And we're going to spend about 1.5 months discovering more about equilibrium. But realize, essentially, in this part, in the beginning, the speed with which the concentration is changing is pretty significant. And then in the part where the equilibrium is established, it becomes static, it becomes constant. And so one would say that the speed with which reactants go through a change, same as the speed with which products are getting formed. So it seems like the reaction has stopped, but it's just that the rates are exactly the same. Okay? Now, let's say I were to show you three graphs. So one graph is here, and the other is kind of like that. And I ask you which one is which. So for this reaction, the N2O5 giving you NO2 and half O2, how would you show? How would you show how would you show which one is which? Hopefully you can say that since the one that goes down, and there's only one reactant, so that's going to be N2O5. Of course, NO2 is going to be formed at a higher rate, higher speed, so that should be your top curve. And the half oxygen, it really should be even further down, but I only had that much room. This one will be for oxygen. So hopefully you can envision that if you have a generic reaction, AA plus BB gives you C moles of C and D of D. Hopefully you can see that you're going to see the change in concentration with respect to time, and 1 over A basically comes from the stoichiometric coefficient. Likewise for B, we have the negative charge because it is a reactant. You are generating B mole, so that's why you have the small letter B, and the delta, capital B over delta T. That gives you the overall rate. So understand this negative charge just means that it's a reactant, so it's going to decrease. C and D will go with a positive sign, but overall rate is always going to be positive. Just realize that. Let's discuss the first and foremost reaction rate and concentration of the reactants. It's important to realize that essentially greater is the concentration of your reactant, better would be the reaction rate. And the reason for that is anytime a reaction is occurring, the reaction occurs basically due to the collisions that occur between the reactant molecules. So let's say you have a container, okay, and you have reactant molecules. Now, if it was just one molecule, maybe it would not be. So let's say this is a concentrated solution, and I have another one, which is a dilute solution. Dilute. And I'm saying that only when these atoms, they kind of interact with each other, they collide with each other, only then they would be able to form the products. Well, what does that mean? Don't you think that the one which is concentrated will have a higher probability that molecules are going to interact with each other, and so greater the number of collisions in unit time, faster the reaction, right? On the other hand, if you consider the dilute solution, of course, they are kind of, oblivious to the presence of each other. And so by the time they see and feel each other's presence, a lot of time has already elapsed. So realize, greater the concentration of the molecules, greater the number of collisions that occur, and only when those collisions occur, some of those are going to be fruitful collisions that will give you products, and so the reactants will be consumed and the concentration will decrease and products will be formed. Realize this is true for whether you have one or whether you have a mixture of two different kind of molecules. So even if it was red and blue reacting with each other, it's the same story. Until and unless those collisions don't take place, the reaction is not going to take place. So high concentration, good thing. High concentration, better rate. Now, I want you to think about that graph that I showed you. In the beginning, it was pretty steep, and then over a period of time, it kind of became flat. What does that mean? Realize, as the collisions are occurring, more and more products are getting formed. So don't you think that the amount of reactant molecules that are present in the system is decreasing over the period of time? And so there will come a point of time when there aren't as many molecules left in the reaction system. And so, of course, the rate is going to die down because the concentration decreases as well. So as the reactants are consumed, the concentration decreases, and hence over a period of time, the reaction rate would decrease as well. Now, of course, theoretically, there can come a time where you would expect that all the concentration of all the reactants, it kind of goes to zero. So the reaction rate should stop theoretically, but we'll discuss in the chapter on equilibrium what actually happens. But at any given point of time, if you knew the concentration and the time, you should be able to determine what is called as an instantaneous rate, and you should be able to determine what is an average rate. So three things that I want to discuss: instantaneous rate, average rate, and initial rate. Of course, initial rate tells you that's at time 0, t equals 0. So you have a curve, you measure the concentration at t equals 0, and that's what you use to determine the initial rate of the reaction. So that's in the beginning, how fast it is. So you can hopefully see that concentration changes rapidly. Instantaneous rate is determined essentially at any instant of time. At any instant of time. So you could pick whether you want to measure at A, or could it be B, or could it be C? And hopefully you can realize that it's going to be different each time. Just to kind of make you understand this situation, let's say you make a trip from Orlando to Tampa, okay? And you start from your home, so there are some city roads. So you go, stop, go, stop, go. You know, your speed is maybe, let's say, 25 miles per hour at one point of time, and then you hit the freeway. Okay, you hit the freeway. Let's say you hit 528 west. That's what you took first, and so the speed limit is 65. You want to drive at 70, that's okay. So now your speed is 70 miles per hour. All right, and then you hit 417 and eventually I-4. Speed limit there is 70. You want to drive at 80, so there comes a point of time when speed limit becomes 80. And then wherever your destination is in Tampa, you know, your speed might go down. It might become 45. It might become 20. It might become 10, so on and so forth. So if you were to determine the instantaneous rate at a specific, very small interval, you would say that it's 25, 70, 45, 80, all over the place. So at each instant, it's a different number. Likewise, when you are measuring instantaneous rate for a reaction, it's going to be different at each instant because the concentration of the reactant doesn't remain same at each instant, so the rate also will keep changing. Average rate, on the other hand, is taken for broader intervals. So you're going to say, I covered 100 miles, not milliliters, miles, 100 miles in, let's say 70 minutes. Okay, minutes. So 100 miles in 70 minutes. So if you had to say what was your speed, you would go 100 miles divided by 70 minutes. And you would do the math. If you had to convert, you would convert, and you would get your average speed. So realize the average rate of a reaction is given for the entire time, 0 to, maybe 2 hours. So that entire time. So usually these are larger intervals. Instantaneous rate, on the other hand, is for smaller intervals. So can you say that average rate and instantaneous rate could be same? Yes. If you wanted to measure average rate at a very small interval, then of course average and instantaneous would start looking exactly the same. Hopefully that makes sense. Let's go forward. Okay, while we were on the topic, I just thought that we can go over a numerical problem. I have given you a reaction. You won't see that in the PowerPoint. The question is that you have hydrogen peroxide. I'm treating that with 3I minus plus 2H plus. That gives you I3 negative and 2 water. You're given that in the first 10 seconds of the reaction, so as you were running the reaction, concentration of iodide decreases from 1 molar to 0.868 molar. You have to calculate the average rate of the reaction in this time, and you have to predict the rate of change of the protons during this time as well. So just first things first, make sure that you're working with a balanced equation, and looks like you are 3 of iodines, 2 H's and 2 is 4, 2 O's on the right hand side. We are good. So it is a balanced reaction. So first off, if you had to write down the expression for the rate, you would say that it would be negative d H2O2, or delta, you can use either two. So d by dt is equal to negative 1 over 3 di minus over dt is equal to negative half dH plus over dt. I'm only doing reactants at this point of time because the information that is given is in terms of only H plus and I minus. If you wanted to, you can of course write the rate in terms of I3 and water if you wanted to do that. But anyway, so we have to determine the rate, and this is my expression. The change is given to be 868. You always go final minus initial, so final concentration is 868 minus 1 divided by 10 seconds was the time interval. 10 seconds. And I'm going to plug this in on my calculator. And this is molar, and this is of course second. So I'm going to plug this in. I'm getting a value of 4.4 times 10 to the power of negative 3 molar per second, or you can say moles per liter per second. Either way is fine. So that's the rate, the average rate during this interval. Now, if you had to determine essentially what is the d by dt of H plus, what would you do? Realize that we know negative 1 over 3 d by dt, di by dt, is equal to half dh by dt. This part we just calculated to be equal to 4.4 times 10 to the power of negative 3. The negative and negative will cancel, of course. Times 2 should be equal to dh plus over dt. So your value should come out to be 8.8 times 10 to the power of minus 3 moles per liter per second. And that's your answer.